Hello, beautiful people. Today I'm going to talk some more physics and let's talk about neutrinos again because they are fascinating. And in regards to neutron decay, so let's throw up that Feynman diagram again. Okay. Neutron, I'm going to make it like a little straighter than it usually is, but just for convenience. Okay, this is a neutron. This is we'll do this neutron. Okay, it's one up and two downs. Right, they neutralize each other. One up, two downs, boop. That makes one mass photon. That makes the other mass photon, which gives us a neutron. So, okay, and then up here we got the proton because the down turns into an up. So it's an up and a down. It's the proton. And then you got like a W boson or something. This is where the W boson comes in this diagram. And then it splits off because you get a neutrino or antineutrino because spin comes off. And you get the electron, which takes up a whole bunch of room and causes pressure. And that's what dark energy is in my model, is that neutron decays. In the neutron decay, that causes the release of both a proton and an electron, both of which are charged particles. Neutron is an undischarged particles. Charged particles exert a Coulomb force, which is basically a pushy outness on things. So that's where we get the gas from. That's why gases take up volume. It's because the electron cloud has got a volume and it takes up as much volume as it can because it's a gas. And this is the premise of that. But today we're going to focus on the neutrino part, which is like this, basically this W boson, right? Because this is the thing that in the standard model, the W boson is the quote unquote particle that induces this change or mediates this change. I don't know how you guys want to phrase it. Okay, so actually, let's do it over here. In my model, we've got one photon of exactly 2 pi, an unreduced Planck, 2 pi Planck length. One photon trapped over its own gravity, because it's that intense. This warped space-time right around it. This is like the minimal singularity. If you do perturbation theory on black holes, like that's why they'll decay, right? Hawking radiation, because they're not really stable unless they have a minimal mass. It's like once they have a certain mass, then they can preserve themselves as an event horizon, as a black hole. It takes a certain quantity, which is actually probably a very important number. And but the other way is the minimal, and this is the minimal, right? Because this fits exactly over one Planck. It's like the wrapping of a Planck. And then a neutron, so a proton has this in the middle, and then it's got a positive charge because space is falling through the singularity, and the negative charge of the electron is basically the compensatory convergence, divergence. It's the divergence caused by that charge. It's reciprocal. In a neutron, there's another photon also in orbit, but this is not a stable orbit, really. It decays after 14 minutes in free space. You know? Only when it's in a very high intensity situation which actually compresses it tighter onto itself because it has more energy now. And this is why I think beam rather than bottle have different numbers. The beam measurement of neutron decay puts it through a series of compression rings, and that gives it energy and restabilizes it. Whereas the bottle method is more passive, and therefore the neutrons decay faster, is my supposition. I don't know if that's actually true, and it could be sort of like supposed from the energy densities of those fields that they use in it. That would be a correlation, because neutrons are only stable in very high energy situations, like a neutron star, high gravity situations, or a nucleus, high gravity situation. They call it strong force, but let's call it gravity. Okay, so we have a neutron. And this neutron now decays, right? So what happens is this second photon peels off, right? It starts to unwrap, basically. Starts to unwrap, right? Until it is sticking radially from the atom. So instead of being a circumference, it's now going to be a radius. Electron orbital radius, actually. That's what it's going to split into. Like that. And this unpeeling process, right? This flinging out of the negative, out, like that, right? Until it's expanded. That unfolding process causes a swirl in space, which I suggest is the antineutrino component of this. The W boson describes this unpeeling process, essentially. But if we look at it, it's like, oh, wait, if that happened, if there was a thing that gets flung off, this will create itself a rotational disturbance in space. Same way that even you just shoot a particle. You have got space, shoot a particle through space like this, right? Here's a particle. Okay? This going through space this way is going to cause flows around that particle. This is my fluid dynamic model of things. This is where I say the W boson is, and also it links up to this sort of unpeeling process as being essentially the physical process cause of neutrinos. Anyways, more thoughts on neutrinos. I know, nuts. Peace.